So we have seen how to execute Prim's algorithm on this example graph. Now let's see the execution of Kruskal's algorithm on the same graph. Recall the basic distinction between Prim's and Kruskal's algorithms. In Prim's algorithm, you have to select your next candidate to add to the minimum spanning tree from the edges that are incident to the current minimum spanning tree, so it stays connected all the way through. In Kruskal's algorithm, that's not the case. You look at the entire graph and you sort the edges according to their costs, and you select the minimums at each iteration as long as you don't have any circuits. Okay, so I'm going to look at the entire graph here. So I have this ones here. Therefore, those are going to be the ones I'm going to add first, as long as I don't have any circuits. So the first one I add here is this one, and then these two I will add afterwards. Again, the order I add these might be random, or it might depend on some certain condition that I use. Now, after ones are added, well, you look at this graph, or look at this minimum spanning tree candidate. It's not a connected graph at this point. I have 6 vertices and 3 edges, but they are not connected. But at the end, it will become a full a connected tree, obviously. But at this point, it may not be connected throughout the execution. Now, when the ones are done, I'm going to move to twos. So I have this one, this one, this one. So I'm going to add those again, and the order depends on your implementation. It could be random, or it could be according to a criterion. And as long as you don't have any cycles, I'm adding those with the cost of 2, which brings me to trees. This one, this one, this one, this one, this one, this one, and this one. For instance, look here. If I select this one, afterwards, I will not be able to select this one because I will have a cycle here. So that's what you need to be careful about. And let's see, I have 6 edges at this point, so I'm going to need 5 more. So select this one, and then this one, and then this one, and then this one. So at this point, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I'm done. Okay, I didn't need to add the 4s or the 5s, etc. Since I have 11 edges here and I have 12 vertices, my tree will obviously have 11 edges. So at this point, I'm done. I do not have any cycles here, and the cost should be minimized. Let's look at the total weight. 3, 2 makes 5, 6, 9, 10, 15, 16, 19, 22, and 24. As expected, the total weight is the same with Prim's algorithm. You see, the minimum spanning tree found here is different. For instance, this one doesn't have this edge, but this has. It depends on my selection criterion. I selected this one on Kruskal's algorithm, but I did not select it here in Prim's. So the resulting minimum spanning tree turns out to be a different one. However, the total weight is the same as expected, because even if the trees are different, the total weights should be the same, so that those are legitimate results. So this is the basic distinction between Prim's algorithm and Kruskal's algorithm. Prim's algorithm keeps the tree structure intact throughout the execution. You add only edges that are incident to your current minimum spanning tree. On the other hand, with Kruskal's, you just add minimum weight edges as long as you don't have any cycles. It may not be a connected graph throughout the execution, but in the final step, it will become a minimum spanning tree. Now, when you look at the complexity of both algorithms, this is a little bit tricky, because the implementation here has an effect on the complexity, because you see you have certain sorting mechanisms throughout. With Prim's algorithm, you need to find the minimum edge that is incident to your current minimum spanning tree. With Kruskal's, you need to sort the entire set of edges according to their weights. So you have to implement them in such a way that these sortings doesn't affect you in an adverse manner. On the other hand, you will have to keep track of which edges you added, etc. So the time complexity of these algorithms depend on the data structures used. I'm not going to go into details. You can look these up, and there are also implementations on these online if you want. But in a general sense, Kruskal's algorithm, this one, can be shown to run in E log V. So E is the number of edges, V is the number of vertices. Prim's algorithm also can be implemented in either V square or E log V or E plus V log V. So these all are different because the data structures used to implement these are different. Therefore, we cannot really say this algorithm has this complexity because it depends on the implementation. So in certain cases, some implementations might be advantages. In other cases, some other implementation might be advantages depending on your requirements. So in general, these are the general limits. But in general, Kruskal can be preferred in typical applications where your graph might not have a certain special type, or it's maybe sparse, or it doesn't have as many edges as some others. On the other hand, if it is a dense graph, meaning that you have a lot of edges, so the average degree of a vertex is large, in that case, Prim's algorithms usually performs better.